Consider a single cantilever of length L as shown in this figure. Here we have taken a load of mg applied at the end of the cantilever, because of which you see the bending of the beam. Here I have taken some point AB, which is of distance dx, and this point A is at a distance of x from the fixed end, and from the free end it is at a distance of L minus x. So now I am going to write the bending moment. The bending moment is given by the force multiplied by the distance. Force is Wmg multiplied by the distance, that is L minus x. So it is equal to W into L minus x, and this can be equated to the bending moment which you derived in the previous class, that is given by Young's modulus y divided by r, the radius of curvature at this point, into the geometric moment of inertia Ig. Okay, so therefore there is one more thing we have to see, that is the 1 by r, that is reciprocal of radius of curvature, is given by the second derivative of y with respect to x, that is y is how much is the depression happening and x is the distance from the fixed end. So that is d square y by dx square is equal to 1 by r. Now I am going to equate it to this from the previous equation. We can write it as w into L minus x divided by yig. So now I have d square y by dx square is equal to w into L minus x by yig. Now what I am going to do is now integrate this. So when I integrate it, I will get dy by dx is equal to w by yig is constant part. So if I take L minus x integrate with respect to x, it will become Lx minus x square by 2 plus some constant of integration c. But if you apply initial condition, that is x is equal to 0 and dy by dx is equal to 0, so we get that the constant c is equal to 0. So now we can take the same equation and integrate it once again. So we get y, if we take this equation and integrate it once again with respect to, so y is equal to w by yig into Lx square by 2 minus x cube by 6, again a plus a constant of integration. So here again, if we apply the initial condition, that is at x equal to 0, the depression y is equal to 0. So if we do that, again we get the constant of integration. Suppose we call it as c2 and here c1. So constant of integration c2 is also 0. So finally we get therefore y is equal to w by yig into Lx square by 2 minus x cube by 6. So here if we take the free end of the cantilever, that at the free end, that is x is equal to L at a distance of L from the fixed end, so x is equal to L, y becomes equal to h. The depression at the free end I have taken it as h. So if we substitute that, we get y is equal to h is equal to w by yig into L is here, L into x is here L, so x L cube by 2 minus L cube by 6. So if you simplify this part by taking LCM of the denominator, you get w by yig into 3L cube minus 1L cube, that is 2L cube by 6. So this is the equation we get for the depression at the free end. We can rewrite here this equation for finding the Young's modulus y of the material of the cantilever, and that is given by therefore w by ig into h, and this part you can simplify here, it becomes L cube by 3, and substitute here w is the load applied at the free end, that is mg, and the geometric moment of inertia for a rectangular beam is given by BD cube by 12, where B is the breadth and D is the thickness of the beam. And if we substitute this in the equation, we get here y is equal to 4 mg L cube by BD cube H. So this is the equation for finding the Young's modulus of the cantilever beam.